Okay, gives me great pleasure to have Anne-Katrin visiting us, and I'm really glad we are actually going ahead with the in-person talk. So Anne-Katrin's visiting from the University of Toronto. For those of you who didn't realize till before yesterday, this was actually not feasible because of weird border restrictions, but like it's not coincidental that we have our first visitor from Canada today, in that the Canada to US border just opened yesterday. So we're glad that you actually made it across, in some sense just in time, and like hopefully things are getting back to some kind of new normal. Now, I've actually never met Anne-Katrin before the talk, but like, so I first ran into this paper back in summer, and it was one of the few times where I sort of saw a paper and I was kind of struck with like I needed to tell everyone about it, and at some point I realized I could have Anne-Katrin over to give the talk and explain about it instead, and I'm sure she'll do a better job. So apologies to anyone I tried to explain the paper to. Hopefully this will be better. But this, so as I mentioned in the mail, this paper it won the best theory paper at EC this year. But it's also building on a line of work which sort of Anne-Katrin's been doing, I think, back from your PhD days, the University of Bonn, just thinking about the role of information in mechanism design, and uncovering a bunch of phenomena which are just completely surprising. So I have now read the previous papers close to like 10 times, and there's a half a page proof where a certain magic happens, which he was trying to explain to me yesterday. I sort of see why it happens, but it's still surprising to me that it is true. So, in that sense, there's something really exciting going to happen at the space of this talk. So please make sure to keep on interrupting her and make sure that you understand what's going on, because there's something magical about, like, this is an incredibly hard problem which a lot of people have thought a lot about and made very little progress in recent times. And it's amazing when we make any progress, but it's even more amazing when there's a completely new way of thinking about it which actually leads us to this progress. So please feel free to continuously interrupt her and make sure that we understand what's going on until we reach the magic. Okay, while you're testing your screen, so does that work? You may need to turn it on. So I think the one other thing which I learned, which I found interesting, was the other thing I found really surprising about this paper was even though I could see what was true, I had no idea why somebody would think about this. So it turns out Anne-Katrin has a background in pure math. So she's coming from a background in algebraic topology and category theory. At some point she decided that was too abstract, and so mechanism design was the less abstract one. This is the second visitor I've had post-pandemic who was doing completely novel stuff in their field, and it turned out even the previous visitor was someone working in category theory. So I guess that's a sign for me that I should learn category theory, but also I should shut up and let Anne-Katrin tell her about her results.
Well, thanks so much. First and foremost for the information. I'm super excited to be here. I really enjoyed all the conversations I had with you so far. Looking forward to even more. Thanks so much for the kind invitation. I think I can't really live up to that, but I'm going to try to do my best to tell you what we're doing in this paper. It's joint work with Rahul Depp, my co-author at University of Toronto. And so, I'm an economist, so I think sometimes my language may be a little bit different, or I may assume something is known that is not as well known for you. So, so please just kind of interrupt me so I can clarify. And I mean, I hope the slides work out, but if it turns out this is not working out, happy to kind of switch and just kind of explain things on the board. The goal is that you kind of see what we're doing and hopefully understand it, and and I'm very happy about any comments and hearing your thoughts. All right, so what we do here is basically the title says it all. We look at a multidimensional screening problem and combine it with biolearning. Multidimensional screening is a very traditional mechanism design problem that simply asks, well, what is the optimal mechanism to sell multiple goods to a single buyer? And this is actually a very classic economic problem, but that is notoriously intractable, in stark contrast to its counterpart for a single item. So we know how to sell the single item. Once there are multiple goods, things become complicated. What we do in this project is we combine it with biolearning, so we throw another layer on there. And so that's a typical like information design problem. So basically in mechanism design, it's usually assumed that buyers know their private information, so that's given. They know their valuation. But if we think about kind of real life, it's somewhat natural to think, okay, before we want to buy something, we at some point learn about like what the value of this object is for us, or at least form like an estimate. So buyers will learn in some way about product values before trading. And so in a very like hand-wavy way, what we do in this project is we say, well, what can we say about multidimensional pricing if we include biolearning into the problem? Let me give you a very rough hand-wavy bird's eye view of what we do in this project. So we look at kind of a standard multidimensional screening problem. There's one seller who has n goods for sale. Buyers types are given by an n-dimensional vector where each of the dimensions is drawn from an interval, theta low, theta high, that is non-negative. And we assume that the joint distribution F, the prior is common knowledge, so buyer and seller know that CDF F. The actual type realization theta is unknown to both the buyer and the seller. There will be an information stage. I will go more into details like how we exactly model that. Roughly put, the buyer will be able to learn about his type through some very, very general signals. So basically, it's possible to choose both the set of signal realizations here as well as what those signal realizations will tell you about the underlying type. And then the buyer privately observes the signal realization and how much of this information structure is known to the seller and what the timing is, that will vary in like 2 questions that we study. And then there's going to be a trading stage where this is kind of our multidimensional screening problem, where the seller will offer a mechanism, wants to maximize his revenue. Buyers choose what to report to the mechanism and payoffs are realized. So I will tell you more details about each of these components once we get to the model. But basically what we want to do is we study the seller optimal mechanism under biolearning in 2 distinct information environments. By the way, I'm sorry that whenever I move my hand, this is happening. It's very distracting. So basically we look at 2 distinct information environments. One is we basically ask, well, what form does screening or the optimal mechanism take in the most advantageous information environment for the buyer? This is timing-wise the environment where first the buyer will receive a signal. The seller will know that information structure, but not the signal realization, and will then choose a mechanism that is a best response, so that is optimal given that signal. We term this the biooptimal outcome, and we then look at a second kind of information environment or timing, where we ask, well, how should a buyer choose a seller choose a mechanism without precise knowledge of how a buyer learns? So think about a seller who knows that buyers have an underlying prior distribution, but the seller does not know how the buyer learns, so does not know what signal that the buyers obtain. So in that case, a seller might be interested in choosing an informationally robust mechanism, so a mechanism that guarantees him the highest revenue guarantee against any possible signal. What does this mean? Basically, that mechanism, if there's, say, an adversarial nature that just chooses for any mechanism that the seller may pick, the worst signal that like minimizes the seller's profit, then basically that minimal profit that the seller can obtain from a given mechanism is the revenue guarantee. And so the seller would want to choose a mechanism where basically nature cannot do much or can do the least against him. So even if nature picks the worst signal for the buyer for him, he still obtains like a revenue guarantee. So it turns out that from a seller's perspective, the first problem is the min-max problem. The second problem is the max-min problem, which we relate both problems and show that in both environments, the optimal mechanism takes some form of pure bundling. Okay? So that's a rough overview and preview of what you're going to see. So just to make sure we're all on the same page and to frame ideas, let me do a quick warm-up and tell you about like multidimensional pricing. Okay? So and why this is somehow like complex as soon as we have two objects. So consider a seller of two goods. It's a very simple kind of setting here. The buyer's valuation for each good is just a uniform distribution. And the value for, the value of each good is uniformly distributed on 0, 1. And the value of the grand bundle is just the sum of the individual components. Right? So most basic setting you can think of. Now suppose the seller, so what could the seller do in this case, right, if you want to sell that? A simple mechanism is the seller could simply sell each item individually, right? So the optimal price for selling an individual item, if the distribution of the buyer is uniform on 0, 1, is to charge a price of 1/2. So that's just the monopoly price, the profit maximizing price. So what you would get if you take P times the probability that the buyer will buy for that price. So that's 1/2. Okay. So in response to that, the buyer may then choose whether he wants to buy one item, and which item, or both items. Okay. So if we illustrate this, we would get something like that, where so this is the value of item 1, of item 2, right? So we have uniform IID, so we have a unit mass on that square. And so basically in the two light blue shaded areas, it's optimal for the buyer to buy one item at price 1/2. In the dark blue shaded area, the buyer buys both items for a price of 1. And so this would give the seller a profit of 1/4 times the price of 1/2, 1/4 times the price of 1, so that should be 1/2. And this turns out to be the optimal separate sales mechanism. Okay. Now, another mechanism you might think of that's very simple is, well, suppose instead that the seller says, well, I'm only going to offer the whole bundle, so either you buy both items or you buy no item. Okay. So you can't buy an individual item. So you might think that's better or worse for the seller. So here in particular, if the seller were to charge a price of 1, right, which is kind of the same price for the pure bundle for the grand bundle that we've seen before, then the seller actually obtains the same profit of 1/2. However, this is not the optimal pure bundling price. But the optimal pure bundling price would be to charge a slightly lower price here, which gives the seller a greater profit. And as you can also see here, the price is slightly lower, and the buyer buys with a higher probability. So this will actually also be beneficial for the consumer. So here we see that both like the sellers as well as the consumer surplus increases as well. Okay. Okay, so that's like two simple mechanisms that we could see in this case. That doesn't seem too complicated yet, right? But so basically this already shows that now that you have basically two items, if you are able to bundle them, right, given that here the pure bundling mechanism is giving a higher profit, this means the seller can screen more effectively. That's like how we usually call that in economics, so can screen kind of the private information of the buyer more effectively. And it does not need to be at the expense of the consumer. Okay. However, then you might ask in this setting, well, what is actually the optimal mechanism? So what turns out to be the optimal mechanism is to offer kind of a mixed bundling mechanism, so to offer the buyer each good for a price of 1/3, and to also offer the grand bundle, so to tell the buyer, well, if you buy both items, you don't pay the sum of this, but you actually get a discount of square root 2/3. And then what we will see here, because the buyer will kind of do what gives him the highest surplus, so what maximizes the value minus the price he pays. He will buy one item in these kind of light blue shaded areas and both in the dark blue shaded area. Okay. So here you see that this is already kind of a somewhat slightly more complex mechanism than separate sales or like pure bundling or what we know like in the one single unit case. However, and this is for uniform IID values and additive values, right? So this is kind of a very simple setting. However, what we actually know from the literature, and there's a huge amount of literature on multidimensional pricing, we know that optimal mechanisms may actually be even more complex. They may be stochastic, so where basically like if your value is somewhere here and this is what you would report, it might be that the mechanism gives you the grand bundle with a certain probability and just one item with a different probability or something like that. So we can have that optimal mechanisms may be stochastic even for independent additive values. So for example, if the lower bound, if you have uniformly distributed items, the lower bound is strictly positive, this can happen. Moreover, it's been shown, so you would not necessarily have to worry much about complex mechanisms if those simple mechanisms like separate sales or pure bundling would give you approximately the same profit, but as Hart and Nissan show, simple mechanism actually might result in a negligible fraction of the optimal revenue. And just kind of to make clear how weird this whole like multidimensional pricing is, I showed you this for like 2 items, right? It's simple. If you extend this to n goods, so if you go for uniform distributed items, IID on 0, 1, to the best of my knowledge, for general n, the optimal mechanism is not known. Okay. So in sum, bottom line here, multidimensional screening is actually hard and somewhat weird, right? So it's some problem where we really don't get tractability, and where how the optimal mechanism looks seems to like really depend on the prior distribution. Okay. So now let me tell you what we are doing here. Okay. As I said, standard multidimensional pricing problem or screening problem. There's a seller who offers one unit of each of n goods for sale. N greater equals 2, no cost of production. There's one buyer with an n-dimensional type. Each of these types is drawn from an interval that is non-negative. F is the joint CDF of these types, and we assume that this allows for a positive density on all of theta. And initially, that type is unknown to both the buyer and the seller. So both buyer and seller only know the distribution F. Okay. We make one important assumption on that prior distribution F. We assume that it's exchangeable. This is essentially a symmetry assumption, right? It requires that for any permutation, the joint distribution of the joint distribution of that permutation is equal to our original distribution F. Okay. What this requires, it requires basically that the marginals are the same in each dimension, but it does generally allow for positive and negative correlation across dimensions, or yeah, for positive and negative correlations. However, it does impose a lower bound on the negative correlation. So it tends towards like positive correlation, and also the dimensions have to be correlated in the same way. Okay, but importantly, this allows, for example, for IID distributed values, but more generally also for like some correlation in the prior. So what we consider as a framework in terms of utilities of the buyer, we consider a framework here that is actually slightly more general than additive values. In particular, we say, given some type, the buyer's value for a bundle is just the sum of the individual components of this bundle multiplied by a factor kappa b, where that kappa b has to be non-negative. We normalize this to the kappa of the grand bundle, so of buying all items to be 1. Okay. And if the buyer does not buy anything, then his payoff is 0. Okay. So this is slightly more general than additive values. If the kappa b's were 1, we would have additive values. You might now be very unimpressed by this payoff function because it does not seem very general. However, most of the multidimensional pricing literature is actually dealing with additive values. So most of this actually assumes additive values. So this is kind of a little bit more general.
So should I think of this kappa b as below 1 or above 1, or it doesn't matter?
So we allow for both.
Is it
yes.
monotone in some way, or it's
No. So basically, this is a normalization that the grand bundle is 1. But basically, so what we do require, we have one assumption. We make this weak-free disposal assumption, which says that for any buyer type, if you want to maximize surplus, or the most efficient thing to do in terms of trading, they should basically always trade, and the buyer should get everything. So the payoff of the buyer for any type of the grand bundle is weakly greater than if he buys any or from any other bundle. But technically, what this form and this particular weak-free disposal assumption implies. So this weak-free disposal assumption puts an upper bound on the kappa b, but importantly, it does not require some kind of monotonicity on those kappa b's. So it is possible that you have 2 bundles where the smaller bundle actually has the larger kappa b. That's allowed. So you could have something where if you have 3 items, you value the first item. You don't really like a bundle of 2, so your kappa b of getting 2 items is 0, but then you value getting all 3 items again. So something like that you could have, or add-on items, for example, where you value the first item a lot and then you don't put as much value on the following items. When our lower bound of the support is strictly greater than 0, this does allow for kappa b to be strictly greater than 1. So it is possible that the kappa b is strictly greater than the kappa of the grand bundle, but only if the lower bound of the support is strictly greater than 0. Yes. Okay.
Do you have some, is an example that would be good to think about beyond additive?
So I think something like add-on items is kind of a... like add-on items. So basically, if you have a car and car tires and window wipers, then basically you have a high value of the car. So your kappa b for 1 item might be, or for say dimension 1 might be very large. But the kappa b's, if you get item 2 or item 3 just individually, is say 0, right? But then and then you're getting item 1 and 2 that has a value for you, item 1 and 3 has a value for you, but getting just item 2 and 3 doesn't have any value for you, and getting all 3 has a value for you. So something like that would, for example, or is something that's sometimes used in economics. Yeah, something like that. Okay. All right. That's just kind of to state the obvious and close the model. So our players are risk neutral. A lot of the information design literature cannot push beyond risk neutrality. And if the buyer purchases a bundle and pays some amount T, then the buyer's payoff is simply his valuation that he obtains from receiving that bundle minus the price he pays, and the seller's payoff is just the transfer the seller receives. All right, so let me tell you how buyer learning works. So the buyer learns about his type theta through a signal. A signal is just a tuple of a set of signal realizations S and a joint distribution G over S and theta, or G as theta here, where the marginal distribution over theta is the prior. Okay? And the buyer will privately observe that signal realization S. So how you can think about this, basically what it allows you to choose both the set of signal realizations, S, capital S, but then also what each individual signal means or tells you, gives you in terms of information about your underlying type theta. Okay? So now a rational player, upon observing some signal realization S, knowing that information structure, the buyer will then use Bayes' rule to form a posterior distribution over his types. And from this, he can basically calculate his posterior estimate. So conditional on observing signal S, what is your estimate value of kind of your type? Okay. Now, what we do, and this you just, so which is by now pretty common. So it is actually without loss, given that we have risk-neutral buyers here, and that our whole model is linear. That we can restrict attention to unbiased signals, where basically that set of signal realizations is the type space, and where the signal realization that the buyer observes is basically this posterior estimate right away. So how you can think about this is basically if we choose any signal and the buyer, upon observing a signal realization, has to do this calculation, we basically say, hey, we can already dump that into the signal. We are doing all this work for the buyer, okay? And one can show that this is actually without loss, okay? So if the buyer now observes the signal realization, he knows that this is kind of his expected type upon observing that signal realization. We thus refer to these signal realizations as the buyer's posterior types. And we hence identify a signal with the induced distribution over these posterior types. So that G will be a distribution over these conditional expectations of the buyer. Okay? So as such, then the set of signals is basically just the set of all these posterior distributions, or these distributions over posterior types that are induced by some general signal. Okay? So in general, what we do here is we allow for very, very general signal. We basically allow the buyer to learn in any way. Okay? Just some examples of this could be the type plus noise, but it could also be that the buyer just learns about each dimension, whether his value is above or below a certain threshold. So there's a ton of signal structures that we allow you, basically any way to learn.
That should be a correlated, like the signal should be for every bundle, what's your expected value? Like there's no, at the moment, you're not sort of assuming the signal is separate along each dimension. So it could actually correlate the items.
So yeah, so we don't assume anything about that. So that S is actually n-dimensional, right? So this is once again an n-dimensional vector. And the signal will determine basically if there's correlation in it or not. So if you start with an IID prior, right, then if I give you perfect information, that signal will also be IID, right?
Sure.
If I give you pure noise, white noise, then this will be perfectly correlated. If I give you anything in between, where maybe I tell you the signal is the sum of the first two item values, that will be there will be some correlation in this. So we're not saying anything about this here. We allow basically for anything. The signal will determine that. Okay, so to wrap up kind of the explanation of the model, How do we define a mechanism? A mechanism we define kind of in the standard way. A mechanism is a set of messages that the buyer can send, an allocation rule that is possibly random, mapping every message into a distribution or a kind of a likelihood to receive each of the various bundles, and a transfer function that maps each of the messages to a transfer or payment for the buyer. The buyer will choose a reporting strategy that maps each of his posterior types to a distribution over messages. That is the best response given that particular mechanism of the seller. So it means it maximizes his expected payoff from reporting kind of if his type is S and he chooses this strategy sigma, which is the best response, then his payoff is basically his expected value on getting the object minus his expected payment. This has to be strictly weakly higher than if he chooses any other sigma. Okay? So the buyer will choose the best response. And we also have an individual rationality requirement, which basically just says we cannot force the buyer to participate in a mechanism that gives him a negative payoff. Okay? There must be some message that gives the buyer a weakly positive payoff. And so then, given a signal, a mechanism M, and a best response, the seller's profit is basically just his expected payments, given that. Okay, so this is pretty standard. And then kind of just two special classes of mechanisms are the ones I mentioned at the beginning. Pure bundling, which means that the seller only offers the bundle of all items, the grand bundle, at a given price. The buyer can only purchase all goods or no goods, and separate sales where basically the seller prices each item individually and the buyer can choose which item to buy. Okay? These are just two very particular mechanisms that are somewhat simple. All right, so finally let me tell you about kind of what we're looking at here and our result. So we refer to a pair of a signal for the buyer and a mechanism for the seller as an outcome. If G is just any signal for the buyer, and M is an optimal mechanism for the seller in response to G. So it's an optimal mechanism for the seller if the buyer were to learn given G. Our goal is to characterize the Biooptimal outcome. So the signal that maximizes the buyer surplus subject to the seller best responding to this, choosing an optimal mechanism given G. So in particular, in our objective function here, we have the information design problem, which is about about what is the optimal signal for the buyer that maximizes his surplus. And the mechanism design multidimensional screening problem is in our constraint. Okay? So if you were to try to solve this brute force, right, then for any G, you would kind of have to calculate the optimal mechanism. So you would have to solve the multidimensional screening problem, which tends to be intractable, and then kind of optimize over that. So that most likely would fail. At least I would not know how to do it. Okay? So we need somehow a trick to do this here. All right, finally. So this is like one of our main results, and it's actually, this is the result which makes all the results that follow in the paper work. Okay? So what we can show is there exists a biooptimal outcome where that signal, G, of the buyer is perfectly correlated across dimensions, which means that if you see any signal realization, it will have the same realization in each of the dimensions. So in a sense, I could only tell you the first dimension, you know, every other dimension will have the same realization. The seller's best response to that signal is a pure bundling mechanism. Basically, under this mechanism, trade happens with probability 1. So given our weak free disposal assumption, this means that all surplus from trade is actually realized here. So this is an efficient mechanism. Okay? So let me just kind of make some comments here to kind of put this into perspective. So you could say, well, why is it not optimal for the buyer to just learn his value? Notice that typically, simply by telling you that the buyer's signal is perfectly correlated, you, in a sense, know he won't learn perfectly. Because, say, if you start from an IID prior, the only way to get noise into this distribution, posterior distribution, or distribution over posterior estimates of the buyer is to include noise in the signal, right? You can always give someone a perfectly correlated signal, just pure noise. That would be very extreme, right? But in general, to get perfect correlation, most likely you will need noise, right? So that seems like it's not necessary, shouldn't necessarily be optimal, because it means that the buyer will sometimes make bad choices, right? Because typically the buyer's purchasing decision will not necessarily be ex post optimal, right? He will sometimes potentially buy when the price is higher than what he would want to pay for this. Now, just a hand-wavy rough intuition of why this is true. Basically, noisy signals, or like the signal.
Sorry, can I ask a question?
Yes, of course.
So if I take the special case of realism, there's only one item, what does your theorem say in that case?
Oh, so if there's only one item, in the one-dimensional case, it is also true that it is not optimal for the buyer to learn fully. So in that case, if you look at the Biooptimal outcome, we can actually say something about the shape of this distribution of the signal, which will be a truncated Pareto distribution. So in particular, that is a distribution that makes the seller indifferent between charging any price of the support on the support of that distribution. So what you will get, I can just draw this, because otherwise I kind of try to draw this into the air. So for example, if you have a uniform prior, then how this G star will look, it will look something like that. So that's for the one-dimensional case. So basically, this will be a kind of a Pareto, follow a Pareto distribution here. So for any price that the seller charges in this interval, his profit will be the same. And in the Biooptimal outcome, he would charge kind of a price equal to the lower bound. So related to that, that's basically where I say there's two types of noise in the signal. So this is true for the single item case. So basically, even for the single item case, the buyer will not learn perfectly. But there is a way in which kind of by introducing noise into the signal, this will, even in the one-dimensional case, result in the seller charging a more attractive price for the buyer. Very hand-wavily, roughly put. You can think about this under monopoly pricing. You would have the seller choose a price of 1/2, right? So, or you can probably not see if I draw here, but say if you have a uniform distribution, you would have a price of 1/2. And so basically everyone, all these types would buy, these types wouldn't buy, right? So whereas under this signal, the buyer buys with probability 1, right? So what the buyer basically does in that signal, or what the type of noise it is, he uses these really low values for which he would not buy here, and mixes those in the distribution in a very specific way that gives you that shape, that makes the seller indifferent between all of these prices. And then that will result basically in the seller being forced to kind of reduce his price to this optimal price for the buyer. Where in a sense,
In the uniform distribution, you mean reduce the price to 0?
no, the price doesn't go to the 0. The price goes to, it's approximately 0.2 for the uniform distribution. So the seller does still get a surplus. So this turns out to be the solution to the min-max problem of the seller. So this is the minimal profit that
But you
this.
said that there's by trade happens is 100%.
Yes.
So it's like 20% probability my die will even below that lower band and
Yes.
yet I die.
Yes.
Yeah.
Because it's a noisy signal. So to give you a very simple explanation of kind of our intuition for this is if you learn perfectly here, right? Then, and the price is 1/2, you would only buy if your valuation is above 1/2. What I could do is I could say like, oh, you actually don't care about like your exact value if it's below 1/2. So let me instead just give you one signal that tells you your value is below 1/2, right? That creates a unit mass, or yeah, on 1/4. So you get something like this. And then now for the seller, in terms of what's the optimal mechanism, optimal price, he can charge a price of 1/2 and sell with probability 1/2, giving him a profit of 1/4, or can charge a price of 1/4, sell with probability 1, so same profit here. So the seller can absolutely charge this price of 1/4, right? Which actually is better for the buyer, right? Because the buyer now, in expectation, it's better for the buyer, because now the buyer buys with probability 1 and pays a lower price than before, right? So basically this kind of has a similar, that kind of has this idea that by mixing in those values into higher signals and hence committing to sometimes buy even if it's not beneficial for you, that can actually allow you to influence the terms of trade in a way that is beneficial. Okay? So in a sense, so that is known from a previous paper. So that was basically my job market paper. So basically then this is kind of now going to the n-dimensional case and saying, okay, now for the buyer can now has, in the n-dimensional case, has a different way to decide, well, does he want to learn about each of the dimensions, right? So does he want to learn, is my dimension in 2 high and 1 low, or is this kind of both in the middle? And so by choosing a perfectly correlated signal, how you can think about this, hand-vaguely intuitively, is, given our exchangeability assumption especially, is I could, as a signal, simply tell you, give you a noisy signal about your sum of item values, so your grand bundle value. Given the exchangeability assumption, the symmetry in there, that does not tell you anything about the dimensions, right? This is a perfectly correlated signal. And so what this does is it shuts down a lot of that additional screening of the seller, right? All these like possibility to use like separate sales and pure bundling and mixed bundling and all of that he has in multiple dimensions. That's kind of killed by the correlated signal because it essentially makes this a one-dimensional problem, okay? However, I want to stress that this is a result. It's not like, so we get this as a result. It's not like an assumption or something like that, which basically says that by giving up like some of that information and learning perfectly about the dimension, right, yeah, you will sometimes make a mistake. But the benefit from shutting down that screening abilities and getting the better terms of trade, having the seller not exploit all of this ability to screen, that turns out in the trade-off to win and for the buyer to actually want to choose that correlated signal. Okay?
Can I make one comment?
Yes.
Sort of following up Eva's question. So that result also indirectly says that for the buyer to not know their own type, they are better off. Which, okay, like, at least like I've read Anne-Katrin's previous paper many times now, I still find that like amazing. There's something magical going on there which allows that, which this is using. Yeah, that is a very valid question to us. If not knowing the type is helpful somehow.
Yeah. Okay, so yes, and so basically there's these like two types of noise in the signal. One is kind of shutting down the multidimensionality in some ways by the correlation, and then the other one will also like determine kind of the shape of the distribution of types. So both of those, like one will make basically pure bundling an optimal mechanism of the seller. This is also not like, of course we have to prove this, and the other one will basically then give you the optimal pure bundling price from the buyer's perspective. Okay, I have 10 minutes. How much? Do I have 10 minutes?
You can go to 5:20 to start with it. Let's say.
Okay.
15 to 17.
Yes. So basically on the perfectly correlated signal, I briefly like mentioned this. Basically, if you think about any signal, this induces a distribution over grand bundle estimates. It also introduces like marginal distributions and a distribution of all smaller bundles, right? But the signal basically allows you to determine all of these distributions, whereas, say, if I only give you the marginals, you cannot necessarily derive the distribution over grand bundle values. For that, I would also have to tell you the correlation in the signal. Okay. So that said, there's typically multiple signals that can induce the same distribution over grand bundle estimates, right? So that kind of give you the same distribution over the sum. In particular, one of these signals is perfectly correlated. This is where our exchangeability assumption comes in the symmetry. Okay, so this is just kind of a lemma that, of course, we also like prove in detail, but which says for any signal, there exists another signal that's perfectly correlated, such that these two signals induce the same distribution over grand bundle estimates. Okay? So basically, just think of this as it will tell you something about the grand bundle value. There might be noise in this. Okay. All right. So let me try to give you an idea of how the proof works. Okay. I'll try to do my very best here. So what we do. Okay. This is kind of constructive, actually, the proof. Start with an arbitrary outcome. So you could throw at me a signal. And let's assume we can determine what the optimal mechanism is there. Okay. So basically, this is an arbitrary signal for the buyer. It's a mechanism that is the best response to that signal of the seller. And pi is simply the profit of the seller if he chooses that mechanism and given that signal. Okay. Now, that specific signal induces some distribution over those grand bundle values. So basically, over the value of the bundle of all items. Okay, this will be denoted by G upper bar. Now, M, the mechanism, is the best response of the seller to that signal G. This means that the profit that the seller obtains from that mechanism has to be weakly greater than the profit that he would obtain from any grand bundle, any pure bundling mechanism. Okay, so basically, if he chooses a pure bundling mechanism with price P, then his profit from this pure bundling mechanism is the price P times the probability that the buyer's value for the grand bundle is weakly greater than the price, right? That's just 1 minus the distribution G of P, plus potentially if there's an atom at that point, okay? So this is just if there's an atom at the point P. Okay? This has to be true for any price P in the support of this G upper bar of this distribution over grand bundle values. Okay? Now, if we solve this for G, so this is greater or equal than 0, so we can kind of drop this. We get that our G of P has to be weakly greater than 1 minus pi over P. Okay? This is simply by rearranging here. And so it turns out this, if you look at this, this is just a Pareto distribution, right? Starting at pi. Okay. So in other words, if you look at kind of this inequality here, this is just kind of formally what it means for this Pareto distribution to first order stochastically dominate our distribution over these grand bundle values. Okay. Importantly, these Pareto distributions, those are isoprofit curves for the seller. So they look somehow like this. I mean, they don't have this truncation point here, but it means that for any price here, the seller would obtain the same profit pi from charging that price. Okay? That's basically exactly that form. Okay. So why am I talking about this? Basically what we're going to try to do now is we're going to try to construct a candidate signal or distribution of these grand bundle values that will do better than our initial G bar. Do better in the sense that it will make the buyer better off. Okay. Then all we have to do after that is we have to say we need to back out a signal that will actually induce that distribution over grand bundle values. And we have to show that it's the best response of the seller to choose a pure bundling mechanism. Okay. So now, since our Pareto distribution first order stochastically dominates our initial distribution G bar over grand bundle estimates, this inequality holds. So this is simply just first order stochastic dominance. We know that this integral is just the mean of the distribution over grand bundle values. So this is, I did not define this. This is the expected value of grand bundle values here. Okay. And now, given that we have our weak free disposal assumption, right, which means that it's the plus maximizing to always trade the grand bundle, then this mean has to be weakly greater than the profit, because that's the maximal surplus. The seller cannot extract more profit than we can make in terms of surplus. That's on the table. You can only get a share there. Okay, so this is obviously no signal. Like how we get to signals now is what is known from the one-dimensional case. And actually, if we're just thinking about grand bundle values now, so we are in one-dimensional space because we basically slice this n-dimensional space and just look at one slice at the grand bundle signals. So any signal of grand bundle values is a CDF on the support n theta low, n theta high, because that's where our sum of values are. However, not every CDF with a support in this interval is a grand bundle signal. So now what is known in the economics literature, or probably also in statistics, is that a CDF H with a support in n theta low, n theta high is a signal, here a grand bundle signal because we're on that space, if F bar, so that's the prior distribution over grand bundle signals, is a mean preserving spread of H. Okay. And this is simply what this formally means to be a mean preserving spread. So this inequality has to be satisfied for every x. And if that x is actually the upper bound, then this must hold with equality. Okay. In particular, if you were to write here the, in particular it means this equality thing means that they have to have the same mean. Okay, that's why we call it mean preserving spread. Now recall, this is just what we had before. Okay, so what we kind of want to do is we want to tweak that signal in a way, or we want to tweak that distribution in a way that ideally gives us the signal, but does not change kind of the profit of the seller or the surplus of the buyer. Okay, so what we can do here is we can basically truncate this. So you have the Pareto distribution. If you truncate it, so basically you choose a point t at which you let this jump to 1, right? That allows you to kind of get the support to be in your interval. And then also by changing that truncation point, you change the mean of the distribution. And potentially if you push it low enough, you also change kind of the second order condition. But it turns out that second order condition is generally satisfied. Particularly truncated Pareto distributions are supported on pi tau t, and they have an atom here at point t. In particular, if you pick t to be pi, you just get a unit mass from pi. Okay. So now some of you might actually already be like, oh, okay, now I see where this is taking you. So this is just our equation from before up to here. here I just replaced the infinity by n theta h. This is basically if we let the truncation point actually have the upper part of that boundary. It's on this interval n theta low, n theta h. It is just the Pareto distribution. So this is the same value as before. This is the same as before. And now notice that if we have here, if we make the truncation point the pi, this is a degenerate distribution on pi. So this is our pi. Okay. Now if you look at this line, right, you kind of might directly be like, oh, this is just changing the truncation point, right? Intermediate value theorem. So now by the intermediate value theorem, there actually exists one truncation point that we can choose such that, oh, this should be n theta low, n theta high, I'm sorry. Such that this n theta low, n theta high is exactly our mu bar, okay? So that's a condition we need for this to be a to be a signal, right? And then one can show that actually our f upper bar is a mean preserving spread of this. This is kind of what is known from the one-dimensional case and from my previous work, okay? So basically now by having tweaked this to this truncated Pareto distribution, note that if we now look at this grand bundle signal instead of where we initially started from, now trade is efficient, right? If the seller offers a pure bundling mechanism with price equal to the lower bound of the support, right? Because then the buyer will always buy. So that's basically if you now have some distribution like this, and the seller charges a price equal to the lower bound of the support, the buyer will always buy. And the seller still gets the same profit. So we did not change anything about the profit because now the seller sells at a price of pi with probability 1, same profit. Meaning that now we have trade with probability 1, we now realize all surplus, seller gets the same profit, will mean that the buyers, all additional gains from trade have to go to the buyer. So moving to basically the signal will now increase the buyer surplus or make it weakly higher. Okay. So now with this, basically with the lemma I've showed you before, we're almost done. Okay. Now the remaining step is basically recall that by the lemma, there's a perfectly correlated signal that actually induces exactly that distribution over grand bundle values. So this truncated Pareto distribution. And then we can basically rely on a result by Nima and Jason, who basically show that in this case, pure bundling is actually an optimal mechanism for the seller. So the seller wants to best respond in exactly the way that we need here. And that kind of completes roughly the intuition of the proof of that. So in other words, the signal kind of makes this, the particular signal of the biooptimal outcome, that it's perfectly correlated, makes the problem one-dimensional. Okay, I hope you got a rough idea. I'm pretty much out of time. You said I can go till 5:20. So let me just briefly tell you about like the second part of the paper, and maybe flag a couple of things that I want to be very open about. Okay, I think that's kind of how, if you want to interpret this. So some remarks for additive values. It is not the case that pure bundling is the unique optimal mechanism for the seller, but separate sales is also best response. Why do we frame our result in saying pure bundling is the outcome? It's because if these kappa b's are greater than 1 for some proper subsets, one can actually show in a very kind of simple cutesy example that one can argue that separate sales in that case is not a best response for the seller. So, but pure bundling still is. Okay, so in that sense, the pure bundling is what is the robust aspect here, and what always turns, or what in our setting always turns out to be an optimal mechanism. Okay. That's the second part of the paper on the optimal informationally robust mechanism. Just very quickly. you can see kind of, or you can show that if you look at the seller's profit and the biooptimal outcome, this is actually minimizing the seller's profit across all signals. So this is the solution to the min-max problem. So you could also say, well, let's solve the max-min problem. And just from an interpretation, that would mean what mechanism should a seller use that does not know how the buyers learn, and basically think nature or someone might screw them over and have the buyer learn in the worst way for the seller. Okay? In that case, the seller might want to choose a mechanism that provides him with a high revenue guarantee, meaning for any possible signal that could be chosen, this gives him at least a profit of pi. And so we call basically a solution to this problem, to the max-min problem, an optimal informationally robust mechanism, which is defined like that. And here we find that basically random pure bundling turns out to be an optimal informationally robust mechanism. So instead of just charging one price here, what the seller will basically do is kind of choose a price distribution and charge kind of basically randomize over not all of these prices, but one price is like a subset of these prices. Right. So just wanted to kind of mention that. And yes, so basically here the intuition why pure bundling arises is a little bit different. Because basically the seller once again chooses a very simple mechanism and something that somehow makes the problem where he takes the dimensionality out of the problem, right? So now here it's more that the seller wants to kind of ensure himself in like nature using this like multidimensionality against him, okay? So in that sense, here we have kind of exactly the opposite motivation. Why we think this might be interesting is, basically that these simple one-dimensional mechanisms are effective when the seller does not know the type distribution precisely. And maybe that's a reason why we might actually see pure bundling, for example, for digital goods, or why we don't see very complex mechanisms a lot. All right, happy to talk about the literature if you're interested in, but like, let me not, stretch your time more. So we introduce biolearning into multidimensional screening, and I think that's kind of the key point. Surprisingly, this actually makes this model tractable, which is really neat. We then show kind of this correspondence between the min-max and max-min problem, which I think I did not get to talk enough about to like make that clear. The seller optimal mechanism in both is pure bundling, and kind of for the biooptimal one, noise in the signal reduces the seller's ability to screen. Yeah, and so that's about what I wanted to talk about today. And thanks so much for your patience, and for me too. Thanks so much for the invitation that I could be here. Thank you.
I guess we can take quick questions. Sean, go for it.
So you showed with the results that offering pure bundles are optimal. So even though you showed the distance, it also means like the constructive type strategy too? Or is still finding the optimal pure bundle price is still hard?
Oh, okay, so I missed the middle. Like in the end, he said, is it still hard to find the optimal pure bundling price?
Yeah.
So, say, if you have all the information that we assume in the model, no, then it's not hard. Does the seller know the underlying prior, in all of mechanism design, right? There's always does the seller really know the underlying prior distribution of the buyer? So you kind of still have the same attack points there, 100%. So you can basically attack like, are these assumptions like how relevant are they for applications? Like, does the mechanism designer really like have all this information? So on these fronts, I would say it's hard, but if you have that information to compute this, it's not hard. Yeah.
Question or online? Actually, I had a question, although this may be a little longer. So, the fact that the min-max and the max-min are equal here, or at least the form of the mechanism is equal. Like, it makes sense to me generalizing this to other settings is harder, but do you think just that intuition could generalize to other settings?
So basically that the max-min and the min-max problem have the same solution here is not 100% obvious. It's like it's clear that the min-max is an upper bound of the max-min. Basically where that intuition that max-min and min-max have the same solution in this situation, that came from like knowing that from the one-dimensional case. Ben Brooks and Song Chi-do, they have a paper which more generally asks in what situations or under what conditions are the solution to the max-min and min-max problem the same. So they might also have applications in there.
I see, but it's not known, like even under this sort of signaling mechanism, it's not clear. Like there's no clean characterization of when these two problems. Like we don't know when the maximum and min-max, we only know sufficient conditions. But,
yeah, so I mean, Ben and Song Chi's paper, I think they have some of these conditions. They kind of speak to that problem, kind of generally.
This is a crazy
Is there
question.
a connection to strong duality? You know, that's a situation in which min-max and max-min are the same.
Can we?
so I think Peter's question is there a connection to strong duality? Like, do you think there's some more fundamental reason why the two are the same here? Something like a strong duality?
Again, like, I think Ben and Song Chi say, so I know that Song Chi uses that kind of in a one-dimensional case. So it's Ben Brooks and Song Chi do. They basically have a paper where they kind of speak a little bit to that. So I think they are the ones that say most about kind of that relation of the max-min and min-max problem. Yeah.
I'm trying to think how buyers would set up this kind of optimal informational environment for themselves. And I was thinking maybe is insurance some kind of mechanism where like the insurance companies commit to buy things at sort of like prices that are aggregates over buyers. So it's almost like they are operating with like limited information about what each individual buyer wants.
So I think it's kind of really in practice, like how you really set that up. So I mean, in a sense, something like TripAdvisor stuff, right? Like how you frame like what reviews can tell you and whatnot. That can go a little bit in that direction. Also, like if you have a specific way how insurance, say, collects information, yes. Or if you have, I don't know, if you have to send experts to figure out what, I don't know, a certain suggestion for a new Airbus, whatever, like is, and you give them like very strong like criteria how to collect that information. Anything going in that direction, but so how I would consider these. So, I mean, honestly, if you look at this, it's still a quite stylized model, right? So, I would think especially about like the Biooptimal case more as a relevant benchmark, which kind of tells us, okay, how does an optimal mechanism look in kind of the most advantageous environment for the buyer. So if we allow for like the best information environment for the buyer, however we get that, like what would happen, right? And so I think in that sense, maybe the results speak more to like regulators or antitrust people who always say, oh, pure bundling is really bad, like because it harms consumers. So in that sense, this is kind of saying, oh, well, if we're in the most advantageous environment for consumers, this is actually would actually be good for consumers. So I think I would see it more kind of as a benchmark, because I think given that it is such a stylized model, once you go to like applications reality, there's so much factors that you would have to kind of add into it. Yeah.
Thanks, that's super interesting.
Mike has a question online. Go ahead, Mike.
I just wondered, since you said this is such a stylized model, I wondered how strong the exchangeability assumption is that what leaves the multi-dimension to come out of one dimension and the pure bundle strategy. So I was thinking of a sort of first extension of that, where you have a different scaling for each one of the goods, and good 2 maybe the lower band and the upper band are twice as large and so forth, and you have exchangeability subject to scaling. If you thought about what possibly would be strategies in that situation.
So what I can tell you about, like, so exchangeability for the methods that we use here is relevant. So basically what I know is, so what we initially tried was something like, say you have uniformly distribution on 0, 0, 1 in dimension 1, and just a scaled version of that in 0, 2, like in dimension 2, say uniformly distributed 0, 2. And then be like, okay, then kind of what seems to be the natural generalization to perfectly correlated signal is working with co-monotonic signals, right? Like that's just kind of the natural thing to do there, which everything goes through except that lemma where we kind of pull this back, where we have the distribution of the grand bundle values, and then want to pull that back to a signal that induces that. So what does not go through is, so we cannot prove that lemma with our methods. That does not necessarily mean that the results doesn't extend to it, we just like don't know. Because basically the issue we have there is intuitively, if I then would tell you something about the sum of your values, that does not have, as soon as we drop exchangeability, it does not have the feature anymore that it does not tell you anything about the individual dimensions, right? So that's basically, in a sense, that problem that we get there. So the simple answer is we don't know. Yeah, that's the honest answer. I think it's interesting. I would really like to see someone do it, or maybe we'll do it, but we don't know.
I was thinking of a case where the second grid uniform on 0, 2, and if the signal, the exchangeability shows that the distribution on the second component is like twice that on the first. So that you have an exchangeability subject to scaling.
Yeah. So yeah, I don't know. So we tried exactly that example, and we couldn't get a. So it was really something where we thought for a day we could generalize our results to it, to then just come back the next day and be like, oh yeah, our proof is actually not correct because we overlooked that. So it's kind of like a subtle thing where I think what we need is or maybe then your signal is not over the sum. So we basically need a signal over that tells you something about like the grand bundle or something that is really purely one-dimensional and does not tell you anything about the other dimensions. And so I think that's, say if you don't have the same support, right, then we were thinking like maybe you just need the same support to have that. But also if you have different distribution, kind of that feature of the model breaks down.
Okay, I think we should stop and take more questions offline. So let's thank Anne-Katrin again.